Hello everyone. Hope you're all right and having a good break. Right. So last video was about electrophoresis and specific type of electrophoresis. Today we're going to talk about absorption spectroscopy. Okay. So first of all, let's start with understanding what the concept really means. So what is absorption spectroscopy? What does it depending on? So first of all, as you figured out, the last 3 units are about analytical chemistry. So you're trying to figure out what components of a certain mixture you have. Okay, so if you're trying to identify some proteins or some lipids or any molecules, you can do that either through electrophoresis, chromatography, or in this case absorption spectroscopy. So first thing we need to understand is what is a photon. Okay, properties of electromagnetic waves like frequency, wavelength, and energy. Okay, and we also need to understand absorption. So the first part, it focuses mainly on trying to explain that in molecules, in certain molecules that we have in our bodies, or biological molecules, you have bonds. And if you think about it in a very reductive way, bonds are an overlapping of probable areas where an electron can be. Okay, so this is where it starts to get sort of complicated. So this is benzene, first of all, and benzene has a sort of a ring over it. It's not here, but you will see that benzene and other aromatic meaning like cyclic or containing benzene, they'll have a ring like this. Okay, and that contains electrons. Okay, and how we use light and other electromagnetic radiation in order to figure out which bonds you have is by measuring the absorption of that molecule at different wavelengths. Okay, so again, let's start at the very basics. So the electromagnetic spectrum starts at radio waves being the smallest frequency and the highest wavelength, and goes on to gamma rays. I don't know why there we go. Going on to gamma rays, having the highest frequency and smallest wavelength, and also the highest energy per photon. We're going to go on to that later. So first of all, electromagnetic radiation is basically a propagation of waves of alternating electric and magnetic fields. You don't have to think much about that. You don't need to know much about that. But they are basically waves of energy, okay, that contain electrons and also have a magnetic effect. Okay, we can go later into that in quantum physics and stuff like that, but you don't really need to know all of that. All you need to know is that electromagnetic radiation has a frequency and wavelength and energy. Okay, and how we calculate that, and also speed. So all electromagnetic waves have the same speed, which is the speed of light. It's a constant, so it travels at constant speeds, well, approximately constant speeds. And what that speed is, 3 times 10 to the power of 8 meters per second. So it's very fast. Okay, the speed can change when traveling through certain media like air or water or any media. Really, you will see that the wave of the electromagnetic wave, the speed of the electromagnetic wave changes. So how we figure out the speed of an electromagnetic wave is c here is speed. Okay, so they've done a sort of rearrangement here, and all that means is, and v here is frequency. I like to use f, but you can use v as well. So c being frequency times by wavelength. Okay, you might remember this from high school, and all that means is the speed of light equals frequency of the propagation times by wavelength, and it's a constant for all electromagnetic radiation, and it's 3 times 10 to the power of 8. Okay, so now we have the energy. So first of all, an interesting thing to know about electromagnetic waves is they can act as both particles and waves. And what that means is you can, instead of having waves like that, you can also have sort of concentrated masses or balls of energy called photons. Okay, so like we said, a photon is basically like a ball or a unit of energy, and the higher the frequency is, okay, the higher the energy per photon. Okay, so if we use the equation E equals hv, should be hf because f is for frequency, but E equals hv, what that means is the energy per photon is Planck's constant, this is a constant for energy per photon, times by the frequency. Okay, so as the frequency increases, you will see that the energy also increases. Now, what does that have to do with absorption spectroscopy? Essentially, you have different bonds in certain molecules, okay? And these bonds, first of all, one thing you need to know about anything with mass is that it absorbs radiation, it absorbs energy from electromagnetic waves, okay? So you will have these bonds, which we said before, were a field of probable locations of electrons, okay? And these bonds, they're the ones that absorb the energy from the photons. So you will see, let's say if you shine light on this book, for example, the bonds that keep the molecules of paper together, carbon probably, will absorb the energy coming from the photons of the light that I'm using. Okay, and it works the same concept for the molecules. You'll have these bonds, and these bonds will then absorb the photons from the energy, and what that can do is it can excite the electrons. So electrons have something called orbitals and shells and stuff like that. You don't need to know much about that, but what it basically means is that you're giving the electron enough energy to move up an orbital. Okay, so orbitals are kind of levels of energy. If an electron has a certain amount of energy, then it can progress on to the next orbital. Okay, and that causes the spikes in absorption. So let's say if I give a photon energy at 200 nanometers, you won't see that it absorbs it, but not as much. There's like a peak absorbance. So at certain wavelengths, at certain energies, the bonds will absorb the photons of electromagnetic radiation best. Okay, I hope that makes sense. So yeah, I hope that makes sense. Moving on. So now that we know the concept of absorption spectroscopy, there are two terms that we need to know what they mean, okay, that we need to identify. And the first one being chromophores. Chromophores are the chemical groups responsible for light absorption, okay, at certain wavelengths. So let's say you have this molecule, okay, you have a lot of bonds, you have some carbon-carbon double bonds, you have a ring over here, an aromatic ring, and you also have this molecule which I think is, I'm not sure what that is, but you have these molecules, and certain structures, like let's say the rings, will absorb the electromagnetic radiation at certain wavelengths, okay? So these are in turn called chromophores because they are functional groups or groups of, or a certain type of bonds or a certain type of structure, chemical structure that absorbs wavelengths at certain that absorbs light or electromagnetic radiation at certain lengths, okay? And there are other groups which do not absorb the light itself, okay, not at certain wavelengths. So let's say we have a wavelength of 200 nanometers. The oxophore will not absorb the light at 200 nanometers. However, because it's in the same molecule, it will affect the absorption of other groups. So you will see that groups that usually absorb light very well at certain wavelengths will not absorb it as well because of the presence of oxophores. Okay, so like we said, when passing through a sample, light is absorbed, okay, dispersed and transmitted, and you also get reflection, and you get loads of interactions whenever light comes in contact with pretty much anything, okay? So transmittance is basically telling you how much of the light that you gave the sample has exited the sample and how much has been absorbed by the sample at a certain wavelength. Okay, and now how we calculate that is, this is transmittance, by the way. We have the transmitted, or the light that you're feeding onto the sample. Okay, so let's say this pen, I put this pen in front of the source of light. Okay, the light that's coming into it is the light that I'm using. Okay, and what I would have is I would have a sensor just behind the pen. Okay, and it would tell me how much exactly of the light. I can also have the sensors behind the light source in order to tell you how much has reflected. Okay, that's another way. But yeah, you will essentially have a sensor behind this pen, or molecule in this case, and it would tell you how much has been transmitted and how much has been absorbed, and how much in relation to how much is being fed into the pen, okay, or how much radiation I'm putting on to the pen. Okay, so transmittance is the transmitted light intensity, okay, divided by the sample. Okay, so transmitted meaning like the one that is exiting, the amount of light that is exiting the pen, and the amount of light that is divided by the amount of light that's being fed into the pen. Okay, and this is a ratio, so it's from 0 to 1. Okay, you cannot get more absorbed light than there is being fed, because energy cannot be created or destroyed. Okay, same as light. You can't, like, unless you have an inconsistency in your experimental method, it will always be between 0 and 1. Okay, so 0 being it's completely absorbed, so something that is extremely black. Okay, and 1 being 100% no absorption, so a vacuum. Another variable that we can also measure is absorbance. So absorbance is essentially the inverse of transmittance, but there's a twist, okay? And that twist is being the logarithm. So like we said, anything that has logarithmic scale, logarithm in it, or log, okay, that means that it's going up in factors of 10, okay? So that would be whenever transmittance increases by 1, absorbance decreases by 10, because it's an inverse, okay? And what it tells you is it's essentially the inverse. So instead of the light being absorbed divided by the light being fed, it's the light being fed divided by the light being absorbed, okay? So yeah, and because this is a logarithmic equation, is going to always produce a straight line graph, okay, most of the time, and we're going to see that that's not always the case, but anyways, for now. Okay, so now we go on to something called Beer's law, and Beer's law is a function of absorbance, okay? So basically what this says is the absorbance of a certain material equals the absorbativity. So what does absorbativity mean? Absorbativity is a constant for each molecule or substance, and you have two types of absorbativity. You have molar absorbativity, and you have just absorbativity, or the coefficient absorbativity. Okay, so molar absorbativity is C, and coefficient absorbativity is K. So we're going to see that the molar absorbativity is basically defined as how much of light, okay, 1 mole per liter concentration in a 1 centimeter wide cell can this substance absorb. So what does that mean? Let's say I have solution A and solution B. Okay, I can standardize them to have the same volume but different concentrations, and you're going to see different absorbance, not because the substances have different absorptivity, but because they have different concentrations. So concentration is something that affects the absorption of a solution. If you have more molecules, then more of the light is going to be absorbed. Simple as that. And this absorptivity constant is basically saying this is how much of light is going to be absorbed at 1 mole per liter in a 1 centimeter wide cell. Okay, because width here is essentially acting as a measure of volume. Okay, so yeah, then coefficient absorptivity is essentially the same thing, but instead of 1 mole per liter, it's 1 gram per liter. Okay, so when you're measuring concentrations of proteins, you're not going to use mole per liter, you're going to use grams per liter. Okay, so yeah, absorbance is absorptivity times by the concentration, okay, times by the thickness or the width of the cell. Okay, and if you have all three of these values, you can calculate absorbance. Absorptivity is a constant, so more often than not, it's going to be given to you in the question. All right, so here is a rearrangement of Beer's law, which is this. Remember this equation, by the way. Absorbance is absorptivity times by concentration times by width of the cell. So we're also going to have this rearrangement in order to figure out the concentration of a certain molecule in a solution. Okay. Yeah. One more thing. If you've been doing your practicals properly, you're going to notice that you also use a calibrating solution. Okay, and what this calibrating solution is, it's used in order to tell you the value for absorptivity, essentially. Okay, so if you don't have absorptivity and you want to figure out the you want to figure out the concentration of a certain molecule in a solution, you're going to use a calibrator. So you're going to use a standard solution. A standard solution meaning you know the concentration and you know the volume of it. So you're going to know the absorptivity, okay, essentially. And yeah, this is the equation that they've used. Okay, so like we said, if it's showing you where the equation came from. I'm a bit slow today. Yeah, so it tells you here that the absorbance of the calibrating solution over the volume, of course, times by the concentration, okay, is essentially the same as this equation, isn't it? Okay, it's just being rearranged, and it tells you the value for absorptivity. Okay, so absorptivity is the absorbance divided by the concentration of the same solution. If it's a calibrator, you're going to use absorbance divided by concentration, which will give you the value for absorbance, of course, the volume being constant and considered. So yeah, this is also another way to figure out the concentration using the absorbance and the concentration of a certain solution using the concentration and absorbance of another solution with the same molecules in it. Okay, so Beer's law is great, but it does have some limitations that you can only use it when you have lower concentration or concentrations towards the lower end of the spectrum, because when you have higher concentrations, what you're also going to get is you're going to get interactions between the particles of the sample, okay, because you have so many molecules in a very limited space, so the concentration gets higher and therefore they're more likely to interact, okay, and therefore interfere with the value for absorptivity, okay, or even give you a false absorbance for a certain molecule. And yeah, the molecules actually have different intensity of okay, depending on the location. Yeah, so exactly. So some molecules are going to get a lot of exposure to the light source, and some not so much. Okay, so this video is kind of drawing out. I thought it would be shorter. Okay, so yeah, and also another limitation is the quality of the spectrometric instruments. So if you have a faulty sensor, then you're going to get faulty results pretty much. So how do we set up the absorption spectroscopy? So first of all, we use I like to use this diagram because it explains everything very, very well. So first of all, you have visible light. So the light that we see, we know, if you remember from high school or even before that, you will remember the prism experiment, and you will see that when light goes through a prism, it gets diffracted, and what that means is you will get it gets separated into its components. Okay, so visible light is not only just white light, it's white and like this light you get from the sunlight it contains all of the components of the spectrum. Okay, so you get all the colors of light, and if you're acquainted with physics, you will know that different colors of light translate to different wavelengths. Okay, so these different wavelengths are different colors of light. Okay, but we need to use a certain wavelength at a time, okay, to measure the absorbance of the solution at that wavelength of light. Okay, so the first thing that we do is we need to separate the light into its monochromatic light. So what that means is it's unidirectional. Okay, and then we need to separate the light using a diffraction grating into its components, into its wavelengths, into its colors. Okay, and then we can measure the absorbance at a certain wavelength. Okay, so as you imagined, these are the things that you need: a monochromator in order to ensure that the light is monochromatic, meaning in a certain color. Okay, you're gonna have an exit slit. Okay, so this essentially also separates the light into a unidirectional light. Okay, and a laser would be great actually, because a laser is very uniform in its properties, but it's just a single wavelength, so the visible light is a lot better. And yeah, moving on, here it talks about the certain absorption of certain bonds in molecules. Okay, so if we have a colored assay, then, or a colored sample, is going to be pretty standard to measure out the concentration of the molecule, because you know the absorptivity, and you can figure out the concentration using Beer's law. Okay, however, for non-colored or colorless analytes, we do this using another method. So like we said, you have certain bonds and certain areas where electrons might be, and these absorb photons. Okay, so if you at certain wavelengths. Okay, so yeah, this is pretty much repeating what we already said, but what you can also do if you have a colorless solution is you can use stoichiometry. So what does that mean? So let's say if we have molecule A, okay, and this molecule is colorless, and we have a solution of it, and we want to figure out the concentrations. So what we might do is we might react the solution with another molecule. Okay, and what that will give us is a colored product. Okay, and what you notice here is just from this equation, okay, you can figure out, or let's say like that, okay, that's better, that the ratio of A to AB2 is 1:1, and therefore you can figure out the concentration of the original reactant A if you have the concentration of B and the concentration of the product. Okay, and that's exactly what happens in the burette test. So you don't know how much protein there is. So what you do is you react that protein with carbon, okay, to form a colored product, and that colored product concentration can be used to find the concentration of the original reactant, which would be the protein. Okay. So yeah, what else we talk about? Mixtures of proteins and nucleic acids. So we know that pretty much all nucleic acids are present in a mixture with proteins because of either histone wrapping or other proteins essential for the structure of the nucleic acid. Okay, but how do we figure out how much protein compared to? I'm sorry. Yeah, how do we figure out how much protein there is compared to the nucleic acids? Is by figuring out the absorbance of proteins at certain wavelengths and compare that with the absorbance of the nucleic acids for the same wavelengths. Okay, and that gives us a ratio. So let's say the ratio of absorbance at 280 nanometers wavelength compared to 260 nanometers wavelength for proteins which have, by the way, an amide bond is 1.70. And for nucleic acids, the absorbance at 260 compared to 280 would be around between 1.8 and 2.0. Okay, the functional groups that we look for in proteins are not only amide bonds but also phenyl rings. So these are sort of modified benzene rings. You can see in tyrosine, you can see it in tryptophan, phenylalanine. You will see rings of hydrocarbons. Okay, so after we have these two ratios, we can plug that into an equation in order to find out the concentration of protein in the sample compared to nucleic acid. And here it shows you the different absorbance of nucleic acids and proteins at different wavelengths. So you see at 280 is the peak absorbance of proteins, and at 260 is the peak absorbance for nucleic acids. And then we can say, okay, if it's going up this way, okay, so 280 absorbance at 280 is more than 260, then it's a protein. And if it's going down, then it's a nucleic acid. Okay, or if it's going up from this way, then it's a nucleic acid. And then we can figure out these ratio of how much is going up to figure out, well, how much is going up compared to how much is going down to figure out the components. So we can figure out the concentration of proteins and nucleic acid in that sample. Okay, so yeah, these values here are constant. Okay, and it tells you that you can use okay, I just heard. Okay, so it tells you that you also have a factor, okay, from the ratio of absorbance at 280 compared to 260, and that's for the concentration of proteins. Okay. All right. So yeah. So each protein and each molecule for this case has a different absorption coefficient or absorptivity. Okay, or for sorry, the cat just came in. Okay, for a certain protein. Okay, so each protein, you can identify which protein it is by the absorptivity of that protein. Okay, so yeah, here is a table of factors of absorbance at 280 compared to 260 nanometers wavelength compared to the absorbance of it tells you how much percentage of nucleic acid you have. Okay, so here is the the ratio, and you'll see that each ratio contributes to a certain concentration of nucleic acids. Okay, and then you can use these two to figure out the concentration of the proteins. Okay, and that's it for this lesson. Well, for this chapter. Okay, I'll try to do the protocols, but it is a bit tight on time, so we'll see how it goes. Thank you very much for watching, and yeah, come again for chromatography. Thank you.